My sincere greeting to one and all. I am Tamanna from BSc Chemistry Honors second year. Today I am here with chapter Alcohols. First introduction. Alcohol constituent a class of compounds which are regarded as hydroxy derivative of hydrocarbons. They are further classified as mono, di, and trihydric alcohol according as the number of hydroxy group present in their molecule is 1, 2, or 3 respectively. Alcohols containing 4 or more hydroxyl group are known as polyhydric alcohol. Thus, we have methyl alcohol, monohydric, glycol, dihydric, glycerol, trihydric, sorbitol, polyhydric. Hydric. It may be pointed out that di, tri, and polyhydric alcohol always have the OH group attached to the different carbon atom. This is because a compound having more than one OH group linked to the same carbon atom is unstable and at once eliminated in the system. Once eliminated the element of water as shown below, unstable CH3C double bond COH twice, so minus H2CH3CHO. Aromatic hydroxy compound fall into two categories. These are: first is aromatic alcohols. These are the compound in which the hydroxyl group is present in the side chain. They may be regarded as alcohol in which OH group is attached to any aryl substituent, aryl radical. An important example of such a compound is benzyl alcohols, phenol. These are the compounds which contain hydroxyl group or group directly attached to the aromatic ring. For example, phenol is an important phenol. The properties of phenol are marked differently from the properties of alcohol, and their chemistry is discussed separately in chapter 2. Monohydric alcohol. These are the alcohols having the general formula ROH, and R is the simple or substituent alkyl group. Thus, we have methyl alcohol, ethyl alcohol, benzyl alcohol. Saturated monohydric alcohol are also known as alkenols, and as these are the derivative from alkanes by replacement of hydrogen atom by hydroxy group. Alkane can be represented by the general formula CnH2n plus 1 OH, where N is the number of carbon atom. Classification of alcohol. Monohydric alcohol may be further classified as primary, secondary, and tertiary alcohol as given below. First is primary alcohol. These are the alcohol in which the hydroxyl group is attached to the primary carbon atom. For example, ethyl alcohol and propyl alcohol, benzoyl alcohol. It is apparent that the carbon which carries the OH group has at least two hydrogen atoms to it. In the other words, primary alcohol have the characteristic group CH2OH present in them. Secondary alcohol. These alcohol contain the hydroxy group attached to the secondary carbon atom. For example, isopropyl alcohol, secondary butyl alcohol. In these alcohol, the carbon carrying the OH group has only one hydrogen attached to it. As such, the characteristic group in this alcohol is CHOH. Third, tertiary alcohol. These are the alcohol in which the hydroxy group is attached to an tertiary carbon atom. For example, tertiary butyl alcohol. It is clear that the carbon carrying the OH group has no hydrogen attached to it. This means that the characteristic group present in this alcohol is COH. Nomenclature of monohydric alcohol. Monohydric alcohol are by three different systems. First, common system. According to this system, which is used for the simpler alcohol are named by adding the words alcohol to the name of alkyl group present in the molecule. For example, methyl alcohol, ethyl alcohol, and propyl alcohol, isopropyl alcohol, tertiary butyl alcohol, benzyl alcohol. Second, the carbonyl system. According to this system, methyl alcohol is carbonyl and other alcohol are named as alkyl derivative of carbonyl. For example, carbonyl alcohol, methyl carbonyl, dimethyl carbonyl, triphenyl carbonyl. However, this system is used only rarely. Third, the IUPAC system. In this system, alcohol are named in accordance to the journal IUPAC rules. The main point involved in the nomenclature are summed up below. First, longest carbon chain containing the carbon atom carrying the hydroxyl group is selected as corresponding to the parent hydrocarbon. The alcohol is named as derivative of this hydrocarbon by replacing the final E in the name of hydrocarbon by the suffix ol. Third, the parent chain of the carbon atom is numbered for that end, which gives the lowest possible number to the carbon carrying the hydroxyl group. Third, the name of alcohol is then written in other words by writing the name of the side chain or substituent along with their position in alphabetical order, followed by the name of the parent alcohol. For example, ethanol, butane 1-ol, 2-methyl prop 1-ol, 2-methyl propane 2-ol, 2-phenyl ethane 1-ol. Some common and UPSC name of the compounds are methyl alcohol methanol, ethyl alcohol ethanol, and propyl alcohol propane 1-ol, isopropyl alcohol propane 2-ol, and butyl alcohol but 1-ol, secondary butyl alcohol but 2-ol, isobutyl alcohol 2-methyl propane 1-ol, tertiary butyl alcohol 2-methyl propane 2-ol, allyl alcohol prop 2-ene 1-ol. Or this compound have only the IUPAC name for ethyl heptane 1-ol. Structural isomers. Monohydric alcohol exhibit three types of structural isomer. First is chain isomer. This type of isomer is due to the difference in the number of carbon chain attached to the hydroxyl group. It is exhibited by alcohol having 4 or more carbon atoms. For example, butane 1-ol, 2-methyl propane 1-ol. Position isomers. This is due to the difference in the position of hydroxy group in the chain of carbon atom. For example, butane 1-ol, butane 2-ol. In general, the total number of isomeric saturated monohydric alcohol chain can be used well as position isomer is 2 raised to power n-2, where n is the number of carbon atoms. Thus, we have 8 isomeric alcohol having the molecular formula C5H11OH. Functional isomerism. Monohydric alcohol also exhibit functional isomerism, but with another class of oxygen derivative, namely ethers. For example, ethanol, methoxymethane. There are some problems. Write the formula and UPSC name of the alcohol having the molecular formula C2H5 and H12O. So these are pentane 1-ol, 3-methyl butane 2-ol, pentane 2-ol, pentane 3-ol, 2-methyl butane 1-ol, 3-methyl butane 1-ol, 2-dimethyl propane 1-ol, 2-methyl butane 2-ol. Method of formation. Reduction of carbonyl group alcohol can easily be obtained by the reduction of aldehyde ketone and carboxylic acid ester by the variety of reducing agent as follows. First, reduction of aldehyde and ketone. Aldehyde and ketone can be reduced to primary alcohol and ketone to secondary alcohol in number of ways as given below. A. Catalytic hydrogenation. Aldehyde and ketone can easily be reduced to primary and secondary alcohol respectively by hydrogenation in the presence of catalysts such as nickel, palladium, and platinum. This is aldehyde in presence of nickel gives primary alcohol. Ketone in presence of nickel gives secondary alcohol. For example, propenolaldehyde in presence of nickel gives n-propyl alcohol. Catalytic hydrogenation of an aldehyde or ketone contain other easily reducible groups such as carbon-carbon double bond will furnish product in both of the functional group are reduced. For example, crotonaldehyde in presence of nickel and H2 gives n-butyl alcohol. Therefore, this method can be used if it is desired to carry out the selective reduction of only carbonyl group, keeping the group intact. B. Reduction of complex metal hydride. The reduction of aldehyde and ketone to prepare alcohol is usually carried out in laboratory with complex metal hydride such as lithium aluminium hydride LiAlH4 and sodium borohydride NaBH4 aldehyde or ketone in presence of LiAlH LiAlH4 or NaBH4 plus in presence of H3O positive gives primary and secondary alcohol. Sodium boroxide is easier to handle and can be used either in water or alcohol solution. The reduction product initially formed get hydrolyzed to form alcohol. For example, butanol in presence of NaBH4 ethanol and H3O positive gives butane 1-ol. Lithium aluminium hydride react violently with water and alcohol. It can be used only in aprotic solvents such as dry ether or tetrahydrofuran. The product initially formed is then subjected to hydrolysis to get the alcohol. Mechanism: reduction of aldehyde and ketone by both LiLH4 and NaBH4 occurs through the nucleophilic attack of hydride ions on the carbonyl group to form a complex containing OB or OA-Al bond. This species has still got 3 metal hydrogen bond and react further with 3 more molecules of carbonyl compound. The metal oxide intermediate thus formed is hydrolyzed to get the alcohol as shown below. Reduction with NaBH4. There is a mechanism. Reaction with LiAlH4 mechanism. It may be seen that 1 mole of NaBH4 or LiLH4 reduces 4 mole of aldehyde and ketone. Both LiAlH4 and NaBH4 are selective in their reducing action. In this reduction of aldehyde and ketone containing isolated carbon-carbon double bond, only the carbon group get reduced by these reagents. For example, hexane 4-ene-2-on in presence of LiAlH4, NaBH4 or H3O positive gives hexane 4-ene-2-ol. In case of compound which contain carbon-carbon double bond in conjugation with carbonyl group, sometimes the double bond may get reduced along with the carbonyl group. The chance of reduction of the both functional group are more with LiAlH4 than with the NaBH4. For example, gamma phenyl propyl alcohol is made by quinine aldehyde in presence of LiLH4 and H3O positive, where quinine aldehyde in presence of NaBH4 H3O positive give quinine alcohol. Carbon-carbon double bond is not reduced. Thus, NaBH4 is less vigorous and more selective than LiLH4. It may be recalled that a reagent which attacked only one functional group or denote the other's ground which is present is known as regioselectivity reagent. A very effective regioselectivity reducing agent for carbonyl developed recently is 9-BBN-9-borobicol 1,1-nanoone. Mishwar founders. Reduction of carbonyl group acid. Primary alcohol can be obtained by the reduction of carboxylic acid by lithium aluminium hydride. It does not reduce carboxylic acid. In this reaction, the carbonyl part of the carboxylic group is attached to CH2 group. For example, butyric acid in presence of LiAlH4 ether H3O positive gives 1-butanol. Mechanism: the reaction takes place through the formation of intermediate alkoxide which yield the alcohol on hydrolysis. This method is generally employed for the preparation of alcohol from acid which are readily available for natural sources. Carboxylic group acid can also be produced rapidly to primary alcohol by the action of diborans. Third, the reduction of esters. Reduction of esters constitutes the convenient method of preparation of alcohol. This reduction is generally carried out by the following method. First is Bolvat-Valence reduction. This method involves the reduction of ester to alcohol by treatment with sodium in alcohol. The reaction leads to the formation of mixture of two alcohol, one which is formed from alkoxy group or ROH and the second one which is formed from the acyl group RCH2OH ester 2 alcohol. For example, ethyl propanite in presence of NaC2H5OH 1 propanol plus ethanol. Mechanism: this reaction is believed to take place in a number of steps, involve the transfer of one electron at a time from sodium metal as summed up ahead. This is the mechanism. B. The reduction with LiAlH4. Ester can also be reduced with LiAlH4 to yield the mixture of two alcohol, as in case of Bio-Waltz balance reduction. For example, ethyl butyrate in presence of LiAlH4 ether or H3O positive gives 1 butanol plus ethanol. Mechanism: the reaction takes place by the addition of hydride ion in the carbonyl part of ester group. This is followed by the elimination of alkoxide ion to yield an aldehyde intermediate which is not isolated. Further reaction of LiAlH4 with aldehyde gives primary alcohol. Catalytic hydrogenation: one of industrial scale alcohol obtained from ester by catalytic hydrogenation in presence of copper chromatic catalyst. For example, ethyl propanoate gives propanol and ethanol in presence of copper chromate. Fourth, hydrogenation of alkene. Alkene anhydrated to form alcohol either through addition of sulfuric acid or by direct hydration as described. First, addition of sulfuric acid followed by hydrolysis. Alkene react with cold concentrated H2SO4 to form alkyl hydrogen gum sulfate ROSO2OH. Alkyl hydrogen sulfate are easily hydrolyzed by heating with water to form alcohol. This is given alkene plus sulfuric acid give alkyl hydrogen sulfate. In presence of H2O heat gives alcohol. For example, ethylene to ethyl hydrogen sulfate to ethyl alcohol. Propylene first will convert in isopropyl hydrogen sulfate, then H2O presence में isopropyl alcohol. In case of unsymmetrical alkene, addition of sulfuric acid takes place according to Marconi's rule. Direct hydration: the more reactive alkene are directly add to water in presence of acids such as sulfuric acid or phosphoric acid to yield alcohol in accordance with Marconi rule. Alkene to alcohol. For example, 2-methylpropene isobutylene in presence of H positive give tertiary butyl alcohol. Follow Marconi rule. Oxymercuration, demercuration of alkenes. It is a very convenient two-step method for preparing alcohol from alkenes. When treated with mercuric acetate in water tetrahydrofuran solution, alkene from organomercular compound. These mercury compound are reduced by sodium boron hydride NaBH4 to yield alcohol. That is alkene plus mercuric acetate. Oxymercuration THF gives organomercular compound, then give alcohol by demercuration. In this step, first water and mercuric acetate add to the double bond. This is known as oxymercuration. In the second step, sodium borohydride reduces the mercuric compound and the mercuric acetate group get replaced by hydrogen. This is known as demercuration. Both the step takes place very rapidly and conveniently at room temperature. The organomercurial compound formed in the first step is not isolated, but it is reduced in situ by sodium borohydride to form alcohol in high yield greater than 90%. Oxymercuration is highly reagioselective, and alcohol formed is in accordance with Marconi addition of water H and OH to the carbon-carbon double bond. Thus the overall reaction may be summed up as follows. For example, 2-methyl but1 in presence of HgOAc twice THF H2O NaBH4 gives 2-methyl-2-butanol. In writing this reaction, acetate group CH3COO is often abbreviated as OAC. 6. Hydroboration oxidation of alkenes. When treated with diboron BH3 twice, alkene hydrogen undergo hydroboration to form any alkyl boranes. The alkyl boranes are readily oxidized by hydrogen peroxide in alkane solution to form alcohol. Thus, the net result of this reaction also is in addition to water to alkene to form alcohol. For example, ethylene gives borane gives diethyl boranes and then triethyl boranes. The overall reaction can be summed up. Ethylene in presence of BH3 twice H2O2 OH negative gives CH3 CH2 OH ethanol. Hydroboration oxidation is also a research-selective reaction. The alcohol obtained in such if anti-Markovnikov addition of water to alkene has taken place. As such, this method can be used for the preparation of alcohol, which cannot be prepared by other method of hydration of alkenes. For example, propylene gives propanol in presence of BH3 twice and H2O2 OH negative. It may be noted that due to anti-Markovnikov addition, only primary and secondary alcohol can be prepared by this method. Seventh, Grignard synthesis. By far the most important method of preparation of primary, secondary, and tertiary alcohol is by reaction between a Grignard reagent and carbonyl compounds such as aldehyde or ketone. The addition product initially formed by decomposed with water, preferably in the presence of acid such as HCl or H2SO4 to get alcohol. This generated reaction may be depicted as carbonyl compound plus Grignard reagent triether addition product plus alcohol. If the carbonyl compound used in the above reaction is formaldehyde, the final product is primary alcohol. Formaldehyde in presence of triether of RMGX gives primary alcohol. When the carbonyl compound used in some aldehyde other than formaldehyde, the final product will be secondary alcohol. Use of ketone to react with Grignard reagent lead to the ultimate formation of tertiary alcohol. It may be noted that in all these reactions, the number of carbon atom in the alcohol obtained is equal to the sum of the carbon atom in the aldehyde or ketone and Grignard reagent. By the hydrolysis of alkyl halide, the hydrolysis of alkyl halide with an aqueous solution of sodium or potassium hydroxide or moist silver oxidate result in the formation of alcohol. Ninth, by the hydrolysis of ester, the hydrolysis of ester with alkali solution is generally employed for the preparation of alcohols for naturally occurring ester. By the fermentation of carbohydrate, the method is used since very earlier times for the large-scale preparation of ethyl alcohol. The carbohydrate employed in this process is either sugar, used either in form of molasses or obtained from some other source like grapes, beetroot, etc. Some starchy material like potatoes, barley, rice, or maize. This reaction takes place are summarized below from sugar and from starch. The fermented liquor obtained in the above method is known as wash and contains up to 18% ethyl alcohol. It can be concentrated by the fractional distillation. Physical properties of alcohol. Due to the presence of OH group in the molecule, alcohol are polar compounds. Oxygen is more electronegative than either carbon or hydrogen, so in that electron of CO as well as OH bond are displaced toward the oxygen atom. Therefore, the oxygen atom carries partial negative charge while both carbon and hydrogen attached to the oxygen carry partial positive charge. Moreover, like water, alcohol molecule also have a bent shape structure, so that we may represent alcohol molecule as Because of this bent structure and polar nature of CO and OH bond, alcohol possesses considerably dipole moment. The above structural features of alcohol have a strong influence on the physical and chemical properties of alcohol as discussed below. First, physical state. The lower alcohols are colorless liquids having a distinct alcoholic smell and a burning taste. These higher members are colorless, tasteless, waxy solids. Second, associated state hydrogen bonding. Since alcohol contain an hydrogen attached to strongly electronegative oxygen, extensive intermolecular hydrogen bonding exists between alcohol molecule. As a result, alcohol exists in the form of associated molecule and not simply monomeric alcohol molecule. Third, boiling point. The boiling point of alcohol are much higher than those of hydrocarbons on ether of comparably molecular weight as is addictive evident for the following example. The high boiling point of alcohol can be explained in terms of extensive intermolecular hydrogen bonding in alcohol. Large amount of energy is required to break these hydrogen bonds which hold the alcohol molecule together in the associated state. Therefore, alcohol boil at a much higher temperature than alkane, ethers, etc., which do not form intermolecular hydrogen bonds amongst themselves. The boiling point of some isomeric alcohols are in the same order, primary greater than secondary than tertiary. This is because out of isomeric alcohol, primary alcohol are most polar and form hydrogen bonds to the maximum extent of as compared to secondary and tertiary alcohol. With the increase in molecular weight, the boiling point increases regularly. Fourth, solubility. The lower alcohol are highly soluble in water, but the solubility decreases with increase in molecular weight. The high solubility of lower alcohol is due to the formation of hydrogen bond between alcohol and water molecules. The rapid fall in the solubility of higher alcohol is due to the fact that with the increase in molecular size, the non-polar hydrocarbon character of the molecule become more dominating in comparison with the polar OH group. This leads to a decrease in the extent of hydrogen bond formation with water, and therefore the solubility in water decreases. For isomeric alcohol, the solubility increases with increase in branching. This is because of the reason that as the branching increases, the surface area of non-polar hydrocarbon part decreases. The higher alcohol, it may be noted, are some more soluble in organic solvent. Fifth, density. Generally speaking, the density of alcohol is lesser than that of water, although it increases with increase in molecular weight. Problem, arrange the following in order of their boiling point. Chemical properties. The hydroxyl group present in alcohol is very reactive to group, and characteristic reactions of alcohol are the reaction of OH groups. In general, the reaction of alcohol may be divided into the following three categories. First, reaction involving the cleavage of OH bond, ROH. Reaction involving the cleavage of CaOH bond, ROH. Reaction involving both alkyl and hexoxyl group of alcohol molecule. Reaction involving the cleavage of OH bond. The general order of reactivity of alcohol in this type of reaction is primary alcohol, secondary alcohol, tertiary alcohol. Explanation. In the cleavage of OH bond, oxygen in which is electronegative than hydrogen always takes away from both of shared electron. Therefore, the relative reactivity of alcohol in this reaction can be explained in terms of electron releasing I positive inductive effect of alkyl group. As we move from primary to secondary to tertiary alcohol, the number of alkyl group attached to the carbon carrying OH group increase from one to another. Due to this, the electron density around oxygen goes on increasing on moving from primary to secondary to tertiary alcohol. The result is that the electrons of the OH bond cannot be sufficiently drawn towards oxygen, and the ease of cleavage of OH bond decreases. Thus, we have order of reactivity in the reaction involving the cleavage of OH bond is primary alcohol greater than secondary than tertiary. It can be easily understood that methyl alcohol, which has only 3 hydrogen attached to the carbon containing OH group, would be more reactive to all alcohol. First reaction with metal acidic nature. Alcohol react with active metal like sodium, potassium, magnesium and aluminium to liberate hydrogen and form metal alcoholates or alkoxides. For example, ethyl alcohol gives sodium methoxide, tertiary methyl alcohol give aluminium tertiary butoxide. This reaction suggests that alcohol are acidic in nature. This is quite understandable since the OH group contain highly electronegative oxygen atom to hydrogen. Naturally, the OH bond is polarized in characteristics and other allowed the separation of hydrogen as positive ion. However, alcohols are very weak acids, even weaker than water. It is because the alkyl group present in alcohol have an electron releasing inductive effect. This causes an increased electron density around oxygen. This result is the electron of OH bond are not sufficiently drawn toward oxygen and the release of proton is rendered difficult. In other words, the positive I effect of alkyl group make the alcohol weaker acids than water. Comparison of acid strength of primary, secondary and tertiary alcohol. Since the plus I effect would be maximum in tertiary alcohol, which have 3 alkyl group attached to the carbon bearing the OH group, and least in primary alcohol having only 1 alkyl group attached to the carbon of OH bond, the order of acidity of alcohol is primary, secondary and tertiary, decreasing order primary, secondary and tertiary, primary alcohol, secondary alcohol, tertiary alcohol. It is an evident that methyl alcohol would be strongly even when the ethyl alcohol and primary stronger even than ethyl alcohol and other primary alcohols since it has no alkyl group attached to the carbon carrying OH group. Second reaction with Grignard reagent. Alcohol react with Grignard reagent to produce hydrocarbon as shown below. Alcohol Grignard reagent hydrocarbon. For example, methyl alcohol plus ethyl magnesium iodide gives C2H6 and ethane. It may be noted that alkene formed correspond to the alkyl group of Grignard reagent. Third, reaction with the organic acid. Alcohol react with organic acid to form esters. This is slow reversible reaction termed as esterification. It is generally carried out in the presence of concentrated sulfuric acid or hydrogen chloride gas. Acid plus alcohol gives RCOO R dash plus H2O. The reaction is irreversible but in nature, but the equilibrium can be pushed in the forward direction by removing the water from continuously. This is done with the help of an apparatus called Dean and Stark separator. If esterification is carried out in the presence of HCl gas, it is known as Fischer-Spears esterification. For example, acetic acid plus ethyl alcohol in presence of HCl gas give ethyl acetate plus H2O. The mechanism of esterification involves the initial protonation of carbonyl oxygen of the carboxylic acid by the proton released by the mineral acid. As a result, carbonyl compound become more positively charged and readily undergo nucleophilic attack by the oxygen of the alcohol. The resulting intermediate is ultimately converted into the ester as depicted below. Isotopic tracer studies have confirmed that esterification involves the cleavage of OH bond of the alcohol and COH bond of the acid as suggested by the above mechanism. For instance, let us consider the esterification reaction of acetic acid with ethyl alcohol having an isotopic oxygen of atomic weight 18 and hydroxyl group. At the conclusion of the esterification reaction, the isotopic oxygen would be to be present in the ester and not in water, as shown below. Relative reactivity of alcohol and acid. The relative reactivities of alcohols and acid in the reaction are strongly influenced by the steric hindrance caused by the presence of large groups in them. The greater the size of groups near the OH group of the alcohol or COOH group of acid, the slower the rate of esterification. For example, the decreasing rate of esterification of some alcohols and acids are CH3 methanol, ethanol, CH3 twice CHOH, CH3 thrice COH, acid, HC double bond HCOOH, CH3COOH, CH3 twice CHCOOH, CH3 thrice CCOOH. Fourth reaction with acid halide or acid anhydride. When alcohols are heated with an acid halide or acid anhydride, the hydrogen of OH group is replaced by acyl group RCO, and once again an ester is formed. The reaction is known as acylation, takes place more rapidly than esterification with carboxylic acid themselves, and thus we have acetyl chloride with ethanol gives acetyl acetate. It may be noted that in case of polyhydric alcohol, hydrogen of each OH group is replaced by acyl group to form polyesters. For example, 1 molecule of glycerol react with 3 mole of CH3COCl to form triester. Mechanism. The reaction mechanism has been depicted as follows with acid chloride and with acid anhydride. Reaction involving the cleavage of COH bond. In this reaction, the bond between carbon and of the alkyl group and oxygen of the hydroxyl group get repeated. The order of reactivity of alcohol in this type of reaction is tertiary alcohol, secondary alcohol, primary alcohol. Explanation. The above order of reactivity can be also be explained in terms of plus I effect of alkyl groups. As we have moved from primary to secondary to tertiary alcohol, the number of alkyl group attached to the carbon carrying the OH group increases. Due to this, the electron of the COH bond are pushed more and more toward oxygen. As a result, the COH bond become more and more polar and therefore more reactive. In other words, tertiary alcohol would be more reactive in such reactions, and the reactivity of will be lesser and still lesser in case of secondary and primary alcohol. It is also an evident that methyl alcohol would be the least reactive of the alcohols. The first reaction with hydrogen aldehyde. Alcohols react with hydrogen aldehyde to form alkyl halide and water. Alcohol plus HX gives alkyl halide plus H2O. For example, ethyl alcohol in presence of HCl gas anhydrous ZnCl2 gives ethyl chloride. Hydrogen bromide and hydrogen iodide react in same way as shown above in case of hydrogen chloride, but without the presence of dehydrating agent anhydrous ZnCl2. If an alcohol is heated with hydrogen iodide in presence of red phosphorus, it gets reduced to a hydrocarbon. For example, methyl alcohol plus 2HI gives methane plus H2O plus I2. The order of reactivity of halogen acid is HI greater HBr greater HCl, while the order of reactivity of alcohol is tertiary, secondary, primary. Due to its lower reactivity, the reaction of hydrogen chloride with primary and secondary alcohol require the use of catalysts such as anhydrous ZnCl. Due to the difference in the reactivity of primary, secondary, tertiary alcohol with halogen acid, the reaction of HCl with anhydrous ZnCl, also known as Lucas reagent, is used to distinguish between the different classes of alcohol. First, tertiary alcohol react with Lucas reagent intermediately to produce a cloudiness due to the formation of alkyl chloride. Secondary alcohol react with the Lucas reagents less readily to produce cloudiness after 2 to 3 minutes. Primary alcohol react with Lucas reagent only on heating, and no cloudiness is produced in the cold. Mechanism. The mechanism of the reaction is believed to be followed except in some case of methanol and most of primary alcohol. Protonated alcohol or ions. This is obviously an SN1 mechanism involving a protonated alcohol as the substrate and that the halide ion as the nucleophile. The mechanism is supported by the fact that the observed order of relative reactivities of alcohol is same as the order of stabilized of the carbocation. For the formation of rearranged product in many cases further support the intermediate formation of carbocation. For example, neophenylethylene alcohols to triphenylethylene chloride. Alternate mechanism. It has been observed that primary alcohol other than neophenyl alcohol do not form rearrangement product. To account for this, an alternate SN2 mechanism which does not involve the formation of carbocation intermediate has been proposed for ethanol and most of the primary alcohol. Thus we have second reaction with phosphorus aldehyde. Alcohol react with phosphoric aldehyde PCl5, PCl3, PBr3 and PI3 to yield corresponding alkyl halide. Alcohol in presence of PCl5 give alkyl chloride. For example, benzyl alcohol plus PCl5 gives benzyl chloride plus POCl3 plus HCl. For example, alcohol plus PX3 gives alkyl halide plus H3PO3. For example, ethyl alcohol plus PI3 gives ethyl iodide. Mechanism. The mechanism of reaction between alcohol and PX3 may be illustrated by considering the reaction between the alcohol and PCl3 as given below. In the first step, nucleophile attack at alcohol on PCl3 takes place to form a protonated alkyl dichlorophosphate. In the second step, chloride ion act as an nucleophilic and displace HOPCl2 from the phosphate initially formed. HOPCl2 react with more alcohol by the repetition of step 1 and 2 to form RCl and R from the phosphate initially formed. HOPCl2 react with more alcohol by the repetition of step 1 and 2 and form RCl and HO2PCl and further reaction with RCl and OH3P or H3PO3. Thus, the reaction ultimately leads to the conversion of 3 mole of alcohol into alkyl chloride by the 1 mole. The reaction is this. Reaction with thionyl chloride. Alcohol react with thionyl chloride preferably in the presence of base such as tertiary amine to form alkyl chloride. The base promotes the reaction by reacting with HCl. This is tertiary amine plus HCl gives R3NH plus Cl negative. Mechanism. This is believed to take place as follows. Reaction involving both alkyl and hydroxyl group. First, acidic dehydration. When alcohol are heated with sulfuric acid, phosphoric acid or boric acid, or when their vapors are passed over heated aluminium oxide which act as Lewis acid, alcohol get dehydrated to form alkene. For example, ethyl alcohol in presence of H2SO4 433 to 443 Kelvin temperature gives ethylene plus H2O, and butyl alcohol in presence of H2SO4 minus H2O gives 2-butene or 1-butane. The main product formed thus is rearrangement. The reaction between alcohol and sulfuric acid is very sensitive to the conditions of reaction. Distinguish between primary, secondary and tertiary alcohol. Lucas test, the most convenient and commonly used method for distinguishing between different classes of alcohols, is Lucas test. It consists of treatment the alcohol with Lucas reagent with an equimolar mixture of concentrated hydrochloric acid and anhydrous ZnCl. The appearance of cloudiness in the reaction mixture indicates the conversion of alcohol into alkyl chloride. It has been observed that a tertiary alcohol reacts immediately and therefore cloudiness appears immediately. A secondary alcohol reacts within about 5 minutes. When the cloudiness disappears, the primary alcohol does not react with appropriate at room temperature and therefore no cloudiness appears. An older method of distinction between primary, secondary, and tertiary alcohol, also known as Richter-Meyer reagent, is seldom used these days. Dihydric alcohols. Dihydric alcohols are compounds containing two hydroxyl groups attached to different carbon atoms in the molecules. They are also known as diols in IUPAC system, and glycol is commonly system.